Hello, my name is Derek. I'm a student at Forviman College studying mathematics, and today I'd like to tell you about the concept of subsets in mathematics. Specifically, I want to address the question that given a certain set, how many subsets of a certain length are there? How can you count all of these subsets, and how can you enumerate them? My approach, as you see, toward this problem would be recursive through something known as the Pascal's identity. So that we shall prove by giving it a certain interpretation. And that interpretation would also assist us in giving a generative procedure to enumerate all the subsets of a certain set. Now, before we kind of sally forth and talk about the mathematics, I want to give you maybe one or two motivating examples. So let's say you and I are organizing like a conference or a discussion where we want to put people into groups. And then we want to know if we want to try out different arrangements, how many possible arrangements are there? And this question boils down to essentially, it involves counting the different subsets of people we can pick of a certain group size out of the set of all the people, right? And to kind of put a spin on the story, let's say for some apparently good reason, we want to avoid certain groups, or maybe we want to promote certain groups. Then we may want to know the probability that if people sort of form groups randomly, what is the probability of certain groups happening there as well.
Let me also show you an example from science. So here we have the solar system with the sun in the center, and here we are on Earth. Let's say I'm interested in the motion of the Earth in the solar system. Usually, I only consider the interaction between the Earth and the Sun, but surely there are also other planets in the system. And at critical times, they may exert a non-negligible influence on the motion of the planet that I'm interested in. And so, if I allow my calculation to be more complex, I can instead consider a three-body system, the Sun, the Mercury, Venus, or the Sun, the Earth, and Venus. Or I can consider a four-body system. And the four-body system essentially is a subset of four planets that are interacting with each other, or including the Sun. So it may be somewhat useful if I can have a way to enumerate all the possible subsets of planets that can interact with each other. Okay, I think we're now ready to formulate our question mathematically, which involves the concepts of sets and subsets. What is a set? Well, a set is a collection of objects. An example can be a set containing the Sun and the four inner planets, Mercury, Venus, Earth, and Mars. Right? Now, a subset, which is always defined in relation to a set, is a subcollection of the elements in a set. So it contains fewer or all, but definitely not more than the elements in the original set. So I can have a two-element subset consisting of, let's say, the Sun and the Earth in relation to this original set I defined above, or I can have a three-element subset, adding Venus in there. Our question then, in this language of sets and subsets, is that given a set of n elements, how many different subsets of length k, how many different subsets of k elements are there, right? And we may also want to know if there's a way you can systematically enumerate all of these subsets. Now, a preliminary observation I want to make is that the nature of the set, the nature of the elements of the set, doesn't matter essentially to this question, which only concerns the number and the procedure of enumerating all of the elements in a set. Let us now also introduce the essential notation for our problem. So definition, for a set of n elements in a set, the number of subsets of exactly k elements, provided that k is no greater than n, is this quantity denoted here, which we read as n choose k. N choose k meaning that we have n elements in a set, and then we're choosing a subset of k elements. So this quantity denotes the number of all the possible subsets of length k, of k elements. It's also called the binomial coefficient because it shows up in a theorem known as the binomial theorem. So let us familiarize ourselves with this concept by doing a few examples, actually. So I'm going to pick a natural number n, and then what is n choose n? Well, what does this mean? Well, this means I have a set of n elements, and then I'm asking how many different subsets are there that has n elements. Well, in this case, I can only have one set of exactly n elements, which is the original set itself. I can have no fewer, and of course I can have, being a subset, I can have no more. So in this case, there's only one subset, and this is equal to 1. Now, what about some other cases? Let's say I have n elements, and then I'm asking how many subsets of exactly length 1 are there. Well, if a subset only contains one element, then it's just that element, right? So I have n different elements, and I should have n distinct subsets, which only contain a single element. So here it is n. Now here's a more kind of bizarre or kind of more boundary case. So how many subsets are there that has a length of 0? Well, a subset with length of 0 means a subset with no element in it. And by definition, that is an empty set. And there's only one empty set, right? So n choose 0 would be 1. Okay, and this is, again, a somewhat boundary case. But what happens if k, the length of the subset, is greater than the length of the original set? Well, we kind of define this for convenience because this is kind of an ill-formulated problem. Like, how many subsets are there that has somehow more elements than the original set? Well, no, none, right? So this has to be 0 here. With that definition, let us return to our question. So say I have a set A of size n, and then I'm looking to enumerate all the subsets of a certain size k. Each of them has k elements in them. I want to enumerate them. I want to count how many of these subsets there are of exactly k elements. Now let me ask a somewhat leading but maybe non-obvious question at this stage, which is that for any of the subset of a size k, does it contain a special element, some arbitrary element that we can pick? Let's call it mu or something. So, in the case of planets, I can ask, well, does the subset contain the element Mercury in it? Now, any subset would either contain that special element, or it would not contain the special element, right? So I can use this as a criterion, as a binary criterion of classifying sets into those that contains the special element and those that do not contain the special elements. And the total, right, the totality of all the subsets will be a union of the subsets that do contain the special element and the subsets that do not contain that special element. Okay, to write that idea down, I have the set of all the subsets of size k, which we're trying to enumerate. And as we said before, I will use the criterion to classify the sets, which is whether the subsets contain a specially chosen element mu. It really can be any arbitrary element that you can pick. So that gives us the subsets that do combined with the subsets that do not. And this little U symbol means union in terms of set. So what do these sets look like? Well, the subsets that do contain the special element will, each of them will look like, they have contained that element mu. And then I'm going to have some more other elements. So these elements are not mu, and there are k minus 1 of them, because in total I have k elements in the subset that I'm trying to count. And there are going to be other combinations, other subsets that look like this. Okay, and for the subsets that do not contain mu, then, well, they just look like, I have k elements, none of them is mu. Now I want to write this first term slightly differently. So to form a subset that contains mu and k minus 1 other elements, I can express that as a union of a set that contains only mu and k minus 1 elements drawn from the original set, which are not mu, right? And similarly, I'm just re-expressing what I had above here. It's not really changed anything. That I have a set of k elements and that none of them is mu. So now looking at this, a somewhat interesting observation is that we have, in a sense, reduced the problem. right? So our original problem is to count all the subsets of the size k. But then if you look at this first term here, this first set that we're trying to enumerate, we said that all of them contains the element mu. So the enumeration really happens in enumerating all the possible k minus 1 elements which are not mu. So I want to enumerate all the possible subsets of length k minus 1, not including the element mu. And similarly here, right, I have k elements. I want to enumerate the subsets of length k, but then these k elements cannot consist of n. So in other words, I'm drawing from the original set from all the elements except the special element mu, and I'm trying to draw from that n minus 1 element to form all the possible subsets that I can of length k. And to write this down using our notation earlier, we represented all the number, right, the number of all the subsets of size k as n choose k. And now we ask the question, well, does it contain a special element mu? Now for the cases that contain a special element mu, right, I've said that the work I still need to do here is to enumerate all the possible subsets here. All these subsets are drawn from the original set, but with mu removed, because they do not contain mu. And then I'm drawing all the subsets, all such subsets of length k minus 1. So I have n minus 1 choose k minus 1. And then for the subsets that do not contain mu, I'm drawing again from all the element of the original set except mu. But then I'm forming all the length k subsets that I want. So it would be choosing from the n minus 1 elements all the subsets of length k. What we have just shown by ascribing a certain interpretation to the problem is Pascal's identity, which is the relation between the binomial coefficients. And it applies to all values of n and k, provided that they're natural numbers and then n is greater than k. The first observation I would make on Pascal's identity is that it is a recurrence relation. And with the enumerated base case that we discussed earlier, given here again, we can actually evaluate any binomial coefficient that we care to ask for. Well, why is this the case? Well, the basic reasoning is, if you look at the form of Pascal's identity, when you apply it, it gives rise to two further binomial coefficients. Now, the first term preserves the difference between the first entry and the second entry, whereas the second term decreases that difference by 1. So by repetitively applying Pascal's identity, I'll eventually diminish the difference between the first and second entries to no difference at all, in which case I encounter this first base case that shuts off the recursion. Now, for the cases which are not thus shut off by this base case, they have to experience continuous decrease in the second value, in the second entry. And this eventually leads to the base case here, where the second entry becomes 0. The second observation I'd like to make on Pascal's identity is that the interpretation in which we use to arrive at this identity actually provides us with an algorithm, a procedure to enumerate all the length k subsets of the original set. We've actually done this already in our earlier step. I just want to introduce some notation now to make it more explicit. So I'm going to call this enumeration of all the subsets of a certain size k. So it would be a set of subsets, a pick k, in analogy to our earlier binomial coefficient calling n choose k. And I'll skip to the last line here. So essentially what we have to do is we pick some special element mu, and then according to this last step, what I have to generate are all the subsets where I remove the element mu from the original set in which I'm drawing from, right? No mu. And then I am finding all the subsets of length k minus 1, and then I'll be adding mu back into them. And here, it is similar. I will be drawing from the original set A with mu removed, but then I want all the k element subsets. So now if you look at the right-hand side and the right-hand side, we have conspicuously a recursion. And with the sort of similar base cases as we discussed before, we were able to apply this recursive algorithm to enumerate all the subsets of a certain length.
Okay, so this is the gist of what I want to talk to you about, how to count and enumerate the subsets of a certain length given an original set. As a parting comment, I would just like to observe that whereas computationally the recurrence that we've been using, Pascal's identity, and the associated sort of computational counterpart, is feasible, your mathematician friends may not be as satisfied and content with employing that. They may rather prefer an explicit solution, explicit formula for the binomial coefficient without recursion. And in this particular case, there turns out to be a rather straightforward formula for that. So I won't explain it here, but I will deposit a link to a resource in the description that you can check out at your own leisure. But if you want to think about it yourself also, here are some perhaps relevant questions. The first one is, how many sequences of a certain length are there when you're picking from a certain set of objects? And after you have determined that, in a sequence, the order matters, the order of elements matters, but in a set, the order does not matter. So how can you offset these sort of redundant sequences to actually get to the number of subsets from the number of sequences? Okay, but that's for another day. So for now, I just want to thank you for listening.